Hey guys, welcome to Safi Mixed. In this video, I will talk about why the sky looks blue and not violet or indigo. You may have read in your college level physics that the blue color of sky is because of the shortest wavelength of blue light in the visible spectrum. But that's not the only reason. Rather, the blue color of sky is due to three different reasons, and I'm going to explain these three reasons in this video. So I have prepared a presentation, and let's go through that presentation to understand the total story of the blue color of sky. So here I begin by first analyzing the sun visible spectrum, and this is a picture of the sun visible spectrum. You see the wavelengths are in nanometers, and the longest wavelength of 740 nanometer corresponds to red color, and the shortest wavelength that is 380 nanometer corresponds to violet or indigo. And so if we look, the shortest is this one color, and therefore if it is only for the shortest wavelength, then the sky should look violet, but that's not the case. So there are two other reasons along with the short wavelength that gives rise to the blue color of sky. In order to understand that, I first want to share the generalized form of the Rayleigh scattering. And the Rayleigh scattering formula that describes the blue color of wavelength is this one. So I have factorized this formula into different terms: this term, this term, this term, this term, and this term. Overall, there are 1, 2, 3, 4, 5 terms on the right side of this formula. And inside these terms, this small n, in fact, represents the index of refraction of air, and the index of refraction of air is almost same for all colors. So this whole terms for all the wavelengths in the visible spectrum behaves like a constant. Then this is the number density, and we see here rho is a function of height. We know that the number density of atmosphere decreases as we move away from the sea level, but for all the wavelength this change is uniform. That is, if the value of rho h is the same for red and indigo and violet and all the other colors in the spectrum. So this term inside this formula also works as a constant at a given height for all the colors in the visible spectrum. Then this term counts for the angular dispersion, and this is also almost the same for all the wavelengths, so we can treat this as a constant quantity. Then the last two terms, I naught and lambda. This I naught corresponds to the intensity of a particular color or a particular wavelength above the atmosphere, and this is not same for all the colors. Rather, the value of I naught is different for different colors in the visible spectrum. And then we come here to the wavelength. So the wavelengths, we saw from the spectrum that the wavelength of different colors is different, and it is minimum for the violet color. And this I is in fact the intensity of scattered light. So this formula gives us the scattering of a particular wavelength, and this is called Rayleigh scattering. So now I can deal the first term, the second term, and the third term as constant, and I rewrite this equation in a more understandable form by defining another parameter k, which is a function of index of refraction n, the height h, and the angular spread theta. So in the case of atmosphere and for visible spectrum, I can take this term almost constant. And now these two terms, the intensity I naught above the atmosphere and the wavelength of a particular color contribute to the intensity of the scattered light. So treating this K term is constant, I can rewrite this formula into this one form. That is, the intensity of scattered light depends on the intensity above the atmosphere, which I'll call this initial intensity, and the wavelength of that particular color. So now I want to further analyze this by removing this formula. We understood this, and I take this thing to this position, and now I again show the visible spectrum and the percent intensity of Rayleigh scattering. Direct, you see here percent scattering of direct sunlight. So this equation now tells if I first want to observe this equation with respect to wavelength, this equation dictates that the intensity of light scattered would be maximum for the violet or indigo, because those are the shortest wavelength in the spectrum. They correspond to this range. And the scattering for the intensity of scattered light in this region would be minimum. And similarly, for blue light, this range, it is the wavelength is greater than the indigo and violet. So there's the based upon the wavelength, the intensity of violet color would be maximum, and the intensity of blue color would be smaller than as compared to the violet color. And on this basis, the sky should look violet, but we still see it as blue. And here in this plot you see the percentage scattering of direct sunlight. So if we look into this, the percentage scattering for violet in indigo is maximum. It lies at this position, and for blue it starts from this position to this position, it is blue. So this range is smaller than this one range. So basing on the wavelength, the intensity of scattering light is maximum for violet and indigo, but still the sky is not violet or indigo, it is blue. So to see this, let us observe this quantity in the visible spectrum, and that is going like this. This plot shows the relative intensity of different colors and natural sunlight, and we see over here the intensity of violet and indigo is very small as compared to the intensity of blue light, which is typically 1. So the intensity of blue light in the incident sunlight is higher than all the rest of the colors. So these are the two parameters that contributes to the blue color of sky, that is wavelength and the incident intensity, which is maximum for the blue light. There is a third reason, and that's go like this. This plot shows the sensitivity of human eyes to different colors in visible light. And you see the sensitivity is smallest for a red color and also for violet and indigo. So it is very close to 0 or a little higher than 0. But for blue light, it starts almost from this position and going to this position, light blue. So this whole range, the sensitivity of human eyes is higher than violet and indigo, and that's the third reason that the sky does not appear as violet or indigo, rather it appears as blue. So these are the three reasons for blue appearance of sky, that is the wavelength, the maximum intensity of blue light in the incident sunlight, and the relative high sensitivity of human eyes to blue light. Now let me show you a pictorial view that how a human eye catches the blue color of sky. Let me consider this picture, and I have a person standing at this position and a person standing at this position, and this is a particle in the sky, that is an atmospheric particle, and the sun shines to one side of the particle, And here is a white ray reaches the particle. So most of the colors of the white ray passes straight, and the blue light is scattered in all directions, like you see over here. When this scattered light reaches the observer, and if they look at the particle looks blue, because only the blue color reaches the eyes at the ground to the observers looking at the particle. And this way we see the blue color. Thanks for watching.